Hello everyone, I'm Xiaogang. Let's continue talking about these basic concepts. We've probably covered most of them already. Then let's take a look at this interface. Actually, we already created a simple interface earlier. The goal of this lesson is for everyone to read the documentation first. Then we'll implement an interface. Then we'll see how this interface is used. Next, we'll also take a look at where Unreal Engine uses this interface and where else we can find it in mature production level code, how these interfaces are used. How are interfaces used in Unreal Engine? But in practice, we might use them less often. There are interfaces. Actually, they mainly ensure that a group of possibly unrelated classes share a common set of functions under certain functionalities when they might be shared by a large number of complex and different classes. This is very useful. So the meaning of this sentence is very simple. We have discussed the relationship between composition and inheritance. That is, in game development, we often do this. For example, there are many props in the scene. Our NPCs and players have health points. Our props have health points. Our trees have health points. Our buildings have health points. But they may not all derive from the same class, right? You mentioned the monster and the player's character. These two are definitely not the same class. There is no inheritance relationship between them, but they might be derived from the same subclass. Then your item or a building of yours, it also cannot be the same class as this NPC or this monster. They are the same class or have a parent-child class relationship. It's unlikely to be done that way. So to ensure that all these different classes have the ability to query health points, the ability to modify health points, such a function, then we define an interface. There are variables in the interface, or there are some functions like this. Then implement this. So this sentence means we assume there is a system. The trigger volume of this system can trigger a world. This world might be for the user to activate traps or to tell some numbers. Then we define this trigger function and then this function. It specifies that this function is required, but the result of executing this function is different for each class. It only guarantees that every class has this function. Then this function can be extracted into the interface. Let me give you the most common example. I can make everything, every instantiated object, inherit an interaction class, and they all have a collision volume. When we enter this collision volume, we press the E key to interact. If we encounter an NPC, we activate the die. If we encounter a pickable item, we press E to pick it up. This is a simple explanation from the text perspective. So how is it defined? Actually, it is also very clear. They first have a macro called UINTERFACE, then define it as a UClass definition with this macro. Then it has two modifiers. Then there are corresponding metadata tags. Then the class below. Then the name of the interface. Then this public procedural interface. Then this reflection macro. Then note CUXC. It is an empty class, but the actual interface must be written inside another class. It should be written like this. Because it is Yoka, it helps you generate reflection files, and the actual interface you need to write inside the I class. Along with the class above, they are used together as a matching set. Also, it starts with an I. Note this. If you want a blueprint to also be able to inherit it, we know that in blueprints, we can add additional implemented interfaces to a blueprint class. Then you must add the potable specifier. Right here, we can take a look. There's a miniap. He's up to no good again. Okay, so regarding this interface specifier, we mainly need to pay attention to plan table. Meanwhile, this dependency, it has a dependency order. That is to say, you need to know all the things we have written. These reflection classes, they are actually during the engine initialization process, all already registered. Then certainly during registration, there are some dependency relationships and mutual relationships. So you can use dependence to specify it, thus letting the compiler know, when I compile this class, there are actually other classes that need to be compiled first. So that's what it means. So let's look at this code. This is a very normal piece of code, and this is its actor. This actor inherits from actor, and it also implements this interface. So it's public inheritance. Public means you can use everything inside. Public basically means everything can be used. It's public. This is C++ with protected inheritance. Private. These things. We usually write this as public inheritance. And here, it declares for this trigger related thing. Then by default, it is a virtual function. Returns a default. provides a default implementation, returns a default false. So then in the act class, we can override it first, override some related content. Then if you want the blueprint, if this C++ type, you can also override it in Blueprint. Then we use this with, it means that Blueprint can override it. But you need to note, this function cannot be virtual, and this provides a default implementation. The default implementation, that is, this place can call a default C++ implementation. That's what it means. And then this toUnUment, that is, it is equivalent to, let's take a look. That is, we can use C++ to implement it. Then we will complete it in a moment. And finally, that is because we have deflection information, then whether this class implements this interface, we can call its class, get its UI player's object. Then we query whether we pass in another. The UI fetcher passed into this interface. So here within its own ULF information, check whether it records the interface of the implemented parent class. If it does, this information can be obtained. Then this place returns a true. You can also implement it this way. You directly call this implement. This also works. Then this is a cast. This is a type conversion if you have implemented it. Then this app cast should be successful. Otherwise, it will be a null pointer. Yes. Then here it is converted to another Unreal Engine type. This involves multiple type conversions. Then pay attention to the pointer's direction. If it implements all of these, then it can be converted. Actually, to give a simple example, if I am a middle school math book, then this object, if I use a middle school math book pointer, it can point to the current living object, middle school math book. Then I use a middle school book pointer, can point to this object. I use a math book pointer. It can also point to this object. At the same time, the math book pointer, the middle school math book pointer, these two pointers can be converted to each other. Because in fact, this object is a middle school math book, it can satisfy both definitions at the same time. And because it is also a book, I then convert it into a book pointer. That is also to the pointer pointing to this object, converting it into a book pointer. It is also successful. So this part is a bit complicated. This part involves a kind of downcasting. This thing about upward casting, this upload is a bit complicated. We'll write it by hand for everyone in a moment, and then debug it for everyone. This part means you must mark this with red. That's roughly the idea. Okay, now let's implement it. So how do we implement it? Similarly, let's first create a folder here. We'll create it this way. We add an Unreal Engine class. First add an actor class. We add him here. Okay. We add it here. Then we call it interface actor. Just call it this name. Okay, let's take a look. It should be fine. Our face doesn't need to be capitalized. This is the secret method of the two-fang. Then let it refresh the project. Then we might need to copy a few classes over. It should be fine. Okay, let's reload it. Take a look. We can see that he probably doesn't need to go through all the items here. If he only added one class. No problem. Okay. This is the actor for the interface we are using for verification. Then, from the previous place, let's paste a few interfaces over first. Let's check if there are any compilation errors. There shouldn't be any. It's recognized. Let's paste this interface part over here. We mainly want to verify its usage in this family. Then we need to change the name. If you don't change the name, it won't compile right now. Our first interface, let's call it the HealInterface. Then the second interface. Let's call it. We need to change this. Let's call it TypeInterface. It's an interface for querying the actor type. Okay, let's delete these comments now. Because there are too many, they're blocking our view. So we've defined two interfaces here and one actor. Compilation is fine. Okay. Now let's implement this. Let's give it a try and see if we can attach a property. Let's give it an update property and see if it works. It might not work. Maybe we can give it a flow health value. Let's check unload interface. Okay, it fails to compile here, so it seems it's not possible. We cannot reflect this variable to the blueprint. Let's just not reflect it, because it might only allow us to write interfaces. But writing native code works fine. So let's write a simple method. We give it a boolean called IsAlive. And then we make this method virtual. So it can be overridden. Then we can give it a default value. Let's check. It doesn't need it. Its system does. No problem. Now, if we want this actor to have this, we need to write it like this. Then we let it override this method. Paste it over. Okay. Now let me implement it. We give it true. And at the same time, we execute it. Check if there's any issue here. The prompt here indicates that no methods of the parent class have been overridden. It's very simple. It's because we didn't copy the interface correctly. We are inheriting the health interface. So having override is very convenient. If you don't have this override, then it might not be recognized. In this case, you might need to use this eyes. Let me check. I stood in the wrong place again. What am I here for? Right. Need to use ID. This time it succeeded. Then we can call this method in C++. If we need it to be usable in Blueprint, let's just use UFUNCTION directly. Now let's go to Blueprint and see if we can successfully call this method. There's an error here. Let's see what the error is. Because if we want to use Blueprint, we need to remove the virtual keyword It cannot be virtual. So now let's compile again. Let's check what error is reported here. It should be that if the interface is a blueprint query function, but low events should be this query. So it probably doesn't allow doing this. Let's try again. Still doesn't work. Let's look at the error. Oh, then he said it must be done. There is this thing called blueprint event. Okay, then let's just follow the official way of writing this, because the validation is much stricter than before. Before, you could write it however you want it. We'll use this. Okay, let's compile it again. And in this case, then actually it should be no longer possible to write the C++ implementation because it's essentially doing this in Blueprint. Then we should be able to. For Blueprint, we shouldn't give it a default implementation either. Okay, let's try again. Let's take a look at the Blueprint now. Usually, for this interface, we generally don't tend to use Blueprint for it because configuring this thing is a bit complicated. We usually only use it in pure C++ because you can see that Unreal Engine actually has a built-in interface called team, and that interface, so when you often do AI detection, you need to check the neutral side. Only then can you detect some targets. Detect this target, otherwise you won't be able to detect it. And similarly, here we create a new founder called U-interface. Yes, then we create a new level. Similarly, we find the C++ equivalent. We find interface. We inherit this. We give it a BP. And then actually, here we have an over function. Let's see. There should be one. That is it. It's just an interface. Then I can write another class and also have it inherit this interface. When we call this interface, 前成档, that's roughly how it works, right? Just like that. As for the implementation here, we can paste this over as well. Peach should actually be able to provide a C++ implementation. We can paste it over. Then we need to write it again for everyone. Close it. Let's write another one. Let's just keep it dancing. If it keeps dancing, let's take a look. We don't need this category. Let's give it a C++ implementation. This part probably won't compile. Normally, we need to add a suffix. I'll add the suffix word to it. Yes, that's it. So we need this suffix. It prompts here. Is this implementation word already has raw body? This should be that our interface cannot have a default implementation. Then let's keep it as an interface. Let it behave as an interface. Then, in our paper class, we implement it like this. Override. Here, we write override. Okay. We should be able to override it here. Let's note the suffix of this imputation. Yes, this suffix. Let's check what error it reports here. It says it does not override any base class. It should be here. This override should be done like this, right? Over here, the declaration should be fine. Okay, like this, the whole thing. Actually, if you open the blueprint, it should be the same as what we had before. You can take a look. Okay, then let's open this. We can see that here, there should be an override of easy dash. So reflecting this to Blueprint is a bit troublesome, because its syntax is quite different from traditional C++ syntax. Next, let's demonstrate the second one. Also, the second one. We'll also do the second one. This is a type, right? We define this here. Define an enum. We make this enum reflectable to Blueprint. And this enum is like this. We call it xWrite. Then we give it several parameters. The first one is long. The second one is NPC. We give a player. Just giving this arbitrarily. We give a max. Okay, if we hear what to do. We define a function like this. We let this blueprint function be overridable. We use this version. This pure blueprint 1. For blueprint, we still need to specify this interface. Then the name, we return this type. Note, we should not write it inside U. We should write it inside I. It should be written here. The actor type we give. Right, then in this way, it can. As long as it inherits this interface, he can use this function to get the type currently returned by it. Next, we'll have it inherit this interface. Right. We forgot one thing. This needs to be arbitrate. Okay, then let's take a look. Then let's open this. Then here we have this interface. We can implement it. Then here we can select an NPC. Right. Then when it calls the function from outside, for example, GetActorType, right here, it can then get the current what class the actor you touch is. And then you do it like this, and then you don't need everyone to inherit from it. You just need all classes. These classes are unrelated to each other, but as long as they inherit this interface, then you can use this function to get the corresponding what kind of attribute they have. Okay, we'll stop the demonstration of this actor here. Let's demonstrate the code below it for everyone. Let's do a conversion for this. We are in the begin play to perform these conversions, okay? For convenience as well, we'll just write it into begin play. It's simpler. You must call super. I want to emphasize this point. This super must be called. This tick must also be called. Why is that? This is because If you don't call it, then a lot of information for this actor will be incorrect. Because you can see here, this actor has a we found the begin-play negative class. I suddenly saw it, so let me explain it to everyone. Very early. Just now, a reflection didn't seem quite correct. Let's go directly to this place, because you can see this task. It has a set life cycle here. Register all tick functions. Also need to get all components. For each component, it also needs to inject its tick function A. All components need to execute begin play. If you don't execute superior begin play, then none of these things will execute. So you can imagine there will be problem. And this function is very important. As you can see, this function is a doublet point implantable event. It is called begin play in Blueprint. This is your blueprint. Begin play. From this, we can know that the actor's begin play executes before the blueprint's begin play. Then, if our actor returns to this, our actor, if you want it to execute on the blueprint's begin play, you write code here. For example, intercept 2 equals 1. And then do something here. If you want to pass this after the blueprint begin play executes, then you should put it after. We usually do it based on needs. We generally put it after, not to avoid some issues. That is to say, it's like this. Then when we end, we generally like to have an end play. We like to put end play at the bottom. Putting begin play at the top means this. Okay, so what were we about to do? We were just about to paste this code for everyone to see. Let's implement it, and it is the first one. This object of ours, we'll just use this, that is ourselves. We check whether we have implemented this U class. Right, whether we have implemented this interface. Okay, if we have implemented this interface, then this place will be true. That means there is no problem. Then hereby, directly calling this method, we use this method to check whether we have implemented this interface. Okay, so this should also be an error. Then here we directly use a cast to force convert. Let's take a look. But when you convert, be careful. The data being converted here, convert it to an interface of type I. Then here we just give it a z pointer. Okay, let's set the breakpoint here. Set a brain. Okay, so we'll do this here. Let's open our map. Where did our map go? It wasn't saved. Okay. It wasn't saved. Let's create a new map. Same as before. Let's save this map here. Let's call it. It should start with L, actually, to follow proper naming conventions. Interface. Okay. Live interface. Then drag this object in. It will execute begin play. Hey, it doesn't seem to be executing. Let me check. Let's review the code. There is no breakpoint here, right? If there is no breakpoint, we'll check the reason again. Sometimes this situation often occurs. It should not be a big problem. Let's restart the level and compile again. This means the breakpoint is invalid. Let's check if this breakpoint is valid. Whether it is valid, still not valid, then I may need to restart the project. Okay. The breakpoint has been hit successfully here. Let's skip that for now. Let's take another look. Maybe I just opened the wrong observation. Or maybe the project wasn't refreshed. Anyway, just restart and refresh it, and it should be fine. Sometimes it can't find the breakpoint either, which is normal. There's a project in this scene. Okay, let's start it first. Then hit this breakpoint. Okay. Our first judgment. Hey, you see it's not visible here, right? Yeah, it's normal not to see it. So what do we do? Well, let's just kill it. We'll kill it and start it this way. Then we can do it differently here. Another way. Because starting it this way might have a slightly larger performance overhead using by bug game editor. we have explained to you before. Compiling this type, because I use development, it optimized it for us. Let's wait for it to compile a bit. Okay, I'll start it in debug game mode. Now let's set another breakpoint. Let's switch to another map. Now we're back in. Let's take another look. Look here. No problem. Go ahead, no problem. Look, the direction of this pointer is also correct. Okay. Then let's verify next. This piece of code. This code, if I rotate this pointer around, can it work properly, right? Of course it can work properly. Then let's replace this thing. For the fast interface, we first convert it to a black box style. This black box style interface. For the second interface, we convert it to this type of interface. Besides the I note, still in C++ when casting, they are all type I. Okay, then for the pointer here, for the first pointer, let's still use this one, but we cannot redefine it. Let's change it to I object here. Okay, put it here. It is already an interface pointer. Casting it to cat nest first shouldn't be a problem. It's equivalent to executing it once more above. Then we take this object, convert it into another pointer object, and finally, convert this object into an actor. Let's see if it can be successfully recognized. We enter the map. Because we found it, let's go down. Okay, this place succeeded. Look, there is data here too. There is data here too. There is data here too. Okay, so this proves that this conversion is fine. But if we got this pointer from somewhere else, those would have issues. Okay, fine. Now let's expand a bit for everyone. Let's take a look. This thing in Nira. Let's piggyback on Nira, because many things in Nira are wheels that the engine already has. Existing frameworks, we avoid reinventing the wheel. As you can see, this was mentioned before. It has an ability system interface. It defines a method for storing a feature. That is, if you inherit this interface, you must return this AS component. You will find that this actor may hold this ability component. Now let's take a look at this player. Everyone should be very familiar with using player state in Blueprint. Player state will also hold this Lyra system component. This is its overridden AOI overridden method. In addition, you can see that a Lyra target interface is defined here. This interface, he actually didn't inherit the I-interface. He inherited this one. Right? Take a look. Look at ours. For him, this is equivalent to having inherited it once. This interface, it is a class written directly. Here, he mainly inherited the engine's underlying. This agentic tier interface, you will find that there is a set here. There is a set like this, and then here you can get the current team ID. Right? What is this teammate? It is actually just it's just a UNT number. It can be equivalent to having over 200 teams. So this is an interface for creating team. We can usually write it ourselves. It's unlikely to use the engine's one, but if your team is relatively strong, we can also use the engine's one. The engine system is completely fine too, because writing it yourself is a bit more flexible, and it inherits this IGMQ interface. Let's click in and take a look. What does this interface do? This interface is meant to, for those who can use game queue, event service game effect. Speaking of culture, like to form special effects from this effect. And this place is, why is it native only? It's because this blueprint cannot implement these functions that have this native feature. And these need to define how to handle a series of methods for this hand queue. Okay, so what is this? This is an interface for gameplay tag accent. We can see that this interface is used to handle those containing gameplay tags. That is, if this object, he needs to handle this gameplay tag, you can inherit this interface to define modifications. Some matching methods for these gameplay tags. Okay, so this simple UT interface, that's all for now. Good, we have 4 minutes. There's still a little time. Let's take a quick look at the metadata specifiers, since we've already encountered them more or less before. Let's just take a look. Here, actually, our class interface, struct media, then function, properties, it can all add metadata specifiers. Metadata specifiers are specifically for use in our editor when we are developing editor tools. It is very useful. Its definition convention is actually meta. After meta, it is in the form of key value. That is K1 equals K2 equals to do it. In practice, it is often used with class, with media, then interface struct. Use finding property. It looks like this. You can see this is a simple media. So these metadata, you can define its name here. It has these displayed names. Yes. Then the most important thing in the media, there is a hidden thing. It will hide. We take this most important. This everyone, just take a look at these yourself. Start looking. If you don't understand, if you see Chinese and don't understand, then go into the CIG code and do a full text search to see where these things are used. Haven't we just used this thing? This one, right? This display time can be renamed. We'll demonstrate it to everyone. And this hidden. Okay, so let's demonstrate it to everyone. Demonstrate. Mainly demonstrate these two. There's still a bit of time. Then let's find this place. So here we give it a umeta. And then here we give a Blueprint. It has pretty good hints. Not yet dead. So this place, because it is a maximum, is a reserved segment. So here we give it a black one. Let's take a look. In the blueprint, this enum, what does it become? Okay, we can take a look. You will see that this place becomes dead. Originally, we had a max, and it's gone. The largest one is gone. Then, these are some of the interfaces that can be used. Metadata specifiers, right? Then these are the functions. The functions, we have already explained it in detail to you before. That is, we talked about it in the U-function section. There are several most important ones. These display them. Hide pins, or a delay operation. These aspects can be expanded upon in separate small chapters. Later, we will teach you this kind of. That is similar to action, a writing style like action. That is, writing true multi-threading in blueprints, writing true asynchronous operations. These are some metadata tags. It's inside the property. Restrict maximum and minimum values, etc. These kind of things. You can take a look at them yourselves when you get a chance. Okay, so we basically gone through all of these. It wasn't easy. We'll continue with the rest later. Actually, it should be about the same. Actually, this chapter is mainly about covering these topics, and then these simple cases, some commonly used delegates, events, timers, and then some commonly used functions. After the lecture, in fact, the work you can do with Blueprint, most of it can be done step by step. Then we can all smoothly move on to the next chapter. We'll stop here. Thank you all.